Welcome to Lesson 37, Chem 222 Cadets. Today we are going to learn a bit more about the technique of high-performance liquid chromatography. It is the 13th of May. This is Lesson 37. Coming up, Results Report 8 is due on Lesson 38. This is the HPLC analysis of the Vanquish tablet, and that is the 15th of May. So please upload your full results report or the modified one Captain Friday described for you to the team's website. Today we're going to give consideration to the technique of high performance liquid chromatography. This is a very critical method of analysis for biochemical research, so very timely in the days that we are relying on our molecular biologists to come up with a cure for COVID, and how does one go about analyzing samples to detect various chemical constituents. HPLC is the cornerstone technique for a lot of this research that is happening. We're going to look at method selection, instrumental components, the variables that we have to consider before choosing our column, our stationary phase, our mobile phase, and our detection mode, how we go about carrying out successful separations, and what the state of the art is for this method of analysis. To put things in perspective, let's take a look at an instrument that is used to carry out high-performance liquid chromatography. First and foremost, we must have a computer. We are going to have to control a lot of variables that will affect a successful separation. We must, once again, if we are going to separate a sample using a column, and that column contains little tiny particles of silica packed in here nice and consistently. Okay, and we're to get a mobile phase to flow over that packed bed. That's going to require a lot of pressure. So a component in an HPLC is a pump. Okay, and oftentimes these are somewhat sophisticated because we're going to have to adjust the pressures that we use, as well as we're going to have to introduce different solvents into our mobile phase. Oftentimes we're not just using a singular component, but a mixture of several solvents. We must then somehow introduce our sample, so we have to have an injection port. That's what's right here in the diagram. The analytical column is the next featured part of the instrument, and we have to have some means of knowing once our separation is carried out and the components come off the end of the column. We need to know something's coming off, and so we need a detector at the end here. Okay, so in this case, this is an ultraviolet visible absorption detector, just like we learned in our coverage of spectroscopy. So this is just kind of a general layout in your mind of the components in an HPLC instrument. And now we're going to come back and look at some of the specific choices we might make with regard to all of these components. The first thing we need to consider is the nature of our sample and the components within. To select the appropriate method for a separation, we need to start asking ourselves a number of questions, and then following the flow chart shown here. If we are dealing with small compounds and the benchmark is molar masses less than 2,000, okay, then we want to consider this flow chart of decisions. First of all, we ask, are they polar or nonpolar? So if they're soluble in organic solvents, that's the nonpolar side of life. If they're soluble in water, they're pretty polar. Okay, so if our molecules are nonpolar, now we want to ask the extent to which they're nonpolar, and that has to do with solubility in different solvents. So if they are nonpolar to weakly polar, they're going to be soluble in hexane more so than something like methanol. Okay, so coming down this flow chart, if this is the case, we have pretty nonpolar components. The best separation technique is our reversed phase, HPLC. Remember, reversed phase is when the stationary phase is less polar than the mobile phase. Okay, so appropriate stationary phase materials to bond to our silica surfaces are those shown here. If we have nonpolar compounds, but they're not as nonpolar as the previous case, then we're coming down this tree. Okay, solubility in methanol, that kind of thing. And then we want to further discern solubility in different solvents. So if we are soluble in trichloromethane, then we might want to consider doing our separation on a bare silica surface, which does not have a stationary phase material bonded. Once again, that's adsorption chromatography. The best method, if we have solubilities in these solvents, alcohol, acetonitrile, etc., is to do bonded normal phase chromatography. Once again, here, if it's normal phase chromatography, our stationary phase is more polar than our mobile phase. And appropriate groups to bond to our silica surface are those shown there. Coming back, if our sample tends to be polar, we need to know if our constituents are ionic or not. If they are ionic in nature, very simply, we are going to be doing ion exchange chromatography. If they are polar but not ionic, then we are looking at bonded normal phase, in which, once again, we are looking at these types of stationary phase materials to be bonded to our silica surface. So this is the appropriate way to consider what is the most ideal method to separate samples that have a certain characteristic in terms of the polarity and the size of the molecules. If our constituents in our sample are large, that is molar mass greater than 2,000, then we are going to be considering the following techniques. If our constituents are nonpolar, okay, we're going to follow this tree on the left. We're going to ask ourselves, okay, they're nonpolar, how big are they? If we have molecular size less than 30 nanometers, we're going to want to do bonded reverse phase, in which we are considering stationary phase materials such as an octadecyl or an octyl group. If our molecular size is 30 to 400 nanometers, that's getting big enough that now we're going to want to do separation on the basis of size and molecular exclusion chromatography. If our constituents are soluble in water, that means they are polar, or at least more polar than those that are soluble in organics. Once again, we ask ourselves, ionic or neutral. If they're ionic, once again, we're doing ion exchange chromatography. If not, we go through the same kinds of questions about the magnitude of the size of our particles, our constituents. So less than 30 nanometers, we're going to do bonded reverse phase, and greater than that, 30 to 400, once again, we're doing size exclusion. The most common separation done historically, somewhere in the neighborhood of 80% of all separations are done reverse phase. So we're going to focus on what kinds of choices we might have to make in figuring out how to optimize a separation in the reverse phase. So just to demonstrate the complexity of carrying out HPLC as opposed to gas chromatography, there are many parameters we must think about and choose, starting with the nature of our stationary phase material. Okay, are we going to use an octadecimal column or an octal column? What is the diameter of our spherical silica particles that are in our column? What kind of silica are we going to use? There are different purities and acidities of surfaces, so we have to consider that, plus a whole host of other options in selecting our silica. The column itself, the dimensions of the column. How long is it going to be? What is the inner diameter? How much stationary phase material can we get in there? That has to be selected. Then there's the mobile phase. We must select, for the mobile phase, we must select the flow rate. Remember the optimization of the flow rate to minimize plate height and band broadening. Then we must select the mobile phase components. Is it isocratic? That is, are we going to use one solvent throughout? Or are we going to mix several solvents to tweak the polarity of the mobile phase? Then we have the choice of varying the temperature of the separation. Sometimes that's needed and useful. And then obviously we also have to consider the size of our sample to be introduced to the column, and we need to be careful to not overload the column and take up all the parking spaces so that we still get a clean separation. So obviously, carrying out high performance liquid chromatography comes with a fair amount of options and decisions that have to be made about carrying out the separation. It is said that the heart of an HPLC instrument is the analytical column. That is where the actual separation occurs, where our sample components are exposed to the two different chemical environments, the mobile phase and the stationary phase. The analytical column is something that gets purchased from a number of vendors, and a typical column, traditional length and inner diameter, etc., is going to cost you in the neighborhood of at least $400 and could be even more. So it's very important that we not damage the column. Once we develop a method for a particular separation, that is a huge investment of time. So we don't want anything to happen to that column. We want it to last as long as it possibly can. So one thing about our column is that before we let anything flow onto the column, we have all kinds of components in here to protect the column. So, you know, as our sample and mobile phase come through here, mobile phase carrying your sample onto the head of the column. Okay, you oftentimes are going to have what we call a guard column first, because we wish to remove any particulates or anything that can gum up the column. And so we have little porous frits that are going to retain particulates and allow the mobile phase and any reasonably sized components through. The outside of the column is an aluminum jacket. So it's just a rigid container, and inside we have the packed silica particles in there. The industrial manufacturers go to extensive lengths to make sure that the packing is consistent. There's no big voids, pockets of air in there, so that we get ideal flow through. And then at the end, once again, we have another frit that's going to catch anything that might come through that's particulate in nature. And then once the eluent comes off the end of the column, it's going to go on to a detector. Okay, so now, all of the choices we have regarding the materials and the type of column. First of all, starting with the silica support. What kind of silica are we going to use? We have to choose the diameter of the particles. Okay. Most common, they're 5 microns in diameter, but they can go as low as 0.5 microns, 1.7 being probably the most common low-end particle diameter. Silica comes in different pore diameters. So if it's porous silica, we have those channels, the pores. And so what is the diameter of the pore across a pore? Okay, those are typically 60 to 300 angstroms, 60 considered narrow pore, 300 angstroms considered wide pore. What kind of surface area does the silica have? Most common range, 100 to 500 square meters per gram. That surface area is going to dictate how much stationary phase we can bond onto the surface. Okay, so that's an important parameter. The amount of stationary phase on the surface is described as loading. We'll talk about that in a minute. We also can choose different silicas that have different purities. Okay, if we remove contaminants such as metal ions off the surface, we can improve how the support's going to perform. And we'll talk about that later. And then finally, there is a choice in are we going to have traditionally porous silica particles or something known as superficially porous particles. So when you go to purchase a column, these are the kind of options you have in your selection of the silica support. Now, regarding the stationary phase material, options you have are the stationary phase molecules cross-linked or not. Okay, we'll talk about why that's important later. Is the stationary phase end-capped or not? Obviously, we have to choose the R group of the stationary phase. Are we doing normal phase? Is it cyano? If not, if we're doing reverse phase, then we've got a choice of the length of the hydrocarbon chain, or it could be a phenyl group. We also have a choice when we bond to the surface. You've got your R group out here, but you also have a choice of the side groups that are bonded to the silica attached to the surface of the particle. So you have your choice of these groups, the side groups, in addition to the main R group. And then we have to be cognizant of the quantity of the stationary phase on the surface. So the loading is measured in micromoles of the stationary phase per square meter of the silica. And then a last option we have is choosing a material that has a polar embedded phase to protect the stationary phase material. We'll talk about all of these parameters in a minute. And the simple last consideration is the dimension of the column. How long do we need it? And the inner diameter. That's going to dictate how many silica particles are in there. Obviously, cost goes up. If you have a longer and or a wider column, there's more material in there, and it's going to be more expensive. The silica support, once again, is particles of amorphous silicon dioxide. Okay, so the center of the particle, we have these alternating siloxane bonds, silicon, oxygen, silicon. That forms the basis of the core of the particle. Remember that these particles have to withstand high pressures of the mobile phase flowing over them. So it's important that we retain the integrity of the strength of the particle under that high pressure. That's one important consideration about our silica particles. The other is the way that we get our desired stationary phase material onto the surface is we're going to react these surface silanol sites with some kind of a silane molecule to end up getting this kind of chemical modification to the surface. There's our desired stationary phase material. One thing about the silica surface, through 50 years of research, scientists have tried to optimize the reactions so that we react all of the silanol sites on the surface and get rid of them. However, that is impossible to do. So for a number of reasons, we are going to have some unreacted silanol sites on the surface. The nature of these groups, remember oxygen's electron withdrawing, hydrogen is left with a partial positive charge. So these are potential sites of acidity on the surface, which can be bad. If we're trying to separate components such as pharmaceuticals that tend to have a lot of amine groups in them, they're going to hydrogen bond and get stuck on this silica particle. So that is why when we purchase our column and choose our silica support, we need to take into account the extent to which the silanol sites have been reacted and the most ideal protection of our stationary phase so that it does not come off the surface, and a variety of other considerations. So this slide just illustrates the chemical modification reaction in which we get the desired bonded stationary phase on the surface of silica. So here's the surface of our silica particle. Here's our silanol site. We're going to react with some kind of functional silane. In this case, it's a chlorosilane. So we're going to lose HCl and bond the silane to the surface. So we have this siloxane bond right here that's anchoring our stationary phase. Okay, here's our desired R group. Okay, and in the illustration to the right, we've got an 8-carbon long chain, so that's a C8 stationary phase, this long chain here, and the other side groups on my silane, I've got 2 methyl groups out here. So this is, once again, an illustration of what the surface is going to end up looking like after we've modified it with our C8 functionality. So notice that indeed we still do have some of these unreacted silanol sites at different points. Okay, it's a crowded surface, so it's kind of hard for the us to react each and every one of those silanol sites with such a big molecule such as a C8 group. So when you go to purchase your stationary phase for your column, okay, you're going to have a choice, and we went through how one goes about choosing what's most appropriate, but most commonly you can look for, in terms of the R group that's sticking out here, C18, C8, C4 groups, those are very nonpolar. Okay, for other kinds of samples, a phenyl group might be more appropriate. So attached to the surface, we've got a benzene ring, a phenyl group. Then you have cyano or amino or bare silica. And once again, the polarity of the stationary phase has to do with the nature of your sample and which is most ideal for the particular compounds. Before one purchases a column to carry out HPLC, once again, two very important things has to be in one's mind. First of all, the cost of the column. These typically are not trivial in cost, at least $400, and they can be much more depending on the nature, size, etc. So you don't want to be replacing these frequently from a cost perspective. The other perspective is time. It can take upwards of months to develop a method for a specific separation of a specific kind of sample. This is why research and development takes so long. This is why it's unrealistic for a variety of reasons to develop a COVID cure quickly. Just the analysis piece alone is going to take time. So in terms of method development, once we've developed a method on a particular column, we don't want to have to replace our column because a newly purchased column is going to behave a little differently, and so one might have to readdress the development piece. So you want your column to last as long as possible. So we have to be very careful in how we use the column and the things we put on it. One thing to be aware of is when we choose our column, once again, how many unreacted silanol sites are on that column. Those are acidic in nature, so they're going to catch any components that are basic in nature, and once again, a lot of pharmaceuticals are basic in nature. That's going to lead to undesirable peak tailing, where our peaks look like this instead of looking like this, and that's going to limit our resolution. The next thing that can contribute to the acidity is if there's contamination by metal ions on the surface. Okay, so when we choose our silica support, we are also going to look at the acidity and how much purification has gone on to remove any contaminants. We're also going to give consideration to how protected are the siloxane bonds. So once again, when we anchor our stationary phase out here to the surface, the thing that ties the stationary phase to the surface is the strength of this bond right here. We don't want it to undergo attack. Okay, and under extreme conditions, that bond can be vulnerable. If we are at very acidic conditions, low pH, that bond tends to be a little bit more vulnerable, so we may want to protect that bond, and we could protect it by our choice of the side groups that we put on it. The other concern is when you run separations under basic conditions, a high pH. Historically, what happens at high pH is we are going to potentially break the siloxane bonds exposed on the surface, and under the high pressures coming through from the mobile phase, okay, we can actually cause our silica support to collapse. And once the particles within the bed collapse, the performance of the column is going to change drastically, and so we're back to square one, needing a new column and developing a new method. So we want to avoid all of those things. Shown in the lower left-hand corner here is what can happen to the peak shape when we're trying to separate a basic molecule on a column. If we don't do something with the unreacted silanol sites, these acidic groups out here, we're going to get this peak tailing, okay, where some of our molecules get hung up on the column longer. And so to get rid of that, if we can either get rid of these sites somehow or block access to them, we're going to get a much improved peak shape, narrower bands, and better resolution. This slide is intended to demonstrate what a chromatogram would look like if we change the R group for the separation of a fixed set of compounds, okay, with different R groups. So to the left, the chromatogram in figure A is in which the stationary phase is a phenyl group. Okay, we've attached a benzene ring to the silica surface. That tends to be nonpolar. Okay, and in the case of this particular sample, you can see that we get pretty good resolution for all of our components. There's 6 components. We get baseline resolution amongst all of them. The peak shape is decent, so that's an effective separation. What would that separation have looked like if I tried to perform that same separation on a column in which I used a C18 R group on my surface? Okay, obviously this is very nonpolar, but without any aromaticity, pi bonds. Okay, so the same 6 compounds, the resultant chromatogram looks like this. You know, all of our components are coming off, but notice that we have not resolved peaks 5 and 6. So that little distinction in the polarity of the stationary phase material can have an important difference in our resolution of all the components. One option you have when you choose your column for your HPLC separations is whether or not the stationary phase is cross-linked or not. When we carry out the modification reaction of the silica, if we use a di or trifunctional silane instead of a monofunctional silane, so I have in this case 3 chlorine groups instead of 1, then I can actually react 2 silanol sites that are side by the same silane molecule. Okay, and then this group still has a functional site that can react and bond to the side. This results in a silica surface in which we have this cross-linking between our points of attachment of the stationary phase material to our surface. This can help protect the backbone of the silica, and it can protect these bonds that attach the silica to the surface. So the huge advantage of cross-linking is it gets this polymerization of the silane across the surface. It protects the siloxane bonds, so if we need to do our separations at low pH, where it's acidic, okay, we will better protect these siloxane bonds. The disadvantage of stationary phases that are cross-linked, it is a little difficult to control the extent of the polymerization and the nature of the polymerization. So it is difficult for the industrial manufacturers to reproduce that cross-linking from one batch to another. So if you have a column and you've developed your method and it performs in a certain way, and you must replace that column, the next column coming from a different batch could perform differently if it is cross-linked. Yet another option you have when you purchase the silica and your column is whether or not the silica has been end capped. So we initially go in and modify the silica surface, as is the case shown here, with some a C18 group. Okay, so we have our stationary phase attached to the surface, but as I explained, it is impossible to react all of the silanol sites typically with your stationary phase. Once we have placed a big group like a C18 group on the surface, it's going to be really hard to get another C18 group here. But I probably could come back and react those unreacted silanols with something smaller, like a trimethyl group, and that could sneak in and possibly fit in here better. So if I want to end cap, okay, once I've reacted with my initial big R group, okay, I can follow up reacting the surface with something like hexamethyl disialazane or TMCS, which is trimethyl chlorosilane, in which we would have three CH3 groups attached to my silica, and there would be one chlorine for its point of attachment. So either of those modifying reagents are going to put a trimethyl group on this site right here. So the silanol site goes away. I have silicon bond oxygen bond silicon, and then 3 methyl groups sticking out here. Okay, so this is an end capped silica column. And to show how that can be very useful, to the right here are 2 chromatograms. The first was done on a non-end capped column. We are separating basic pharmaceuticals. So amine groups tend to get caught up on the unreacted silanol sites, and you can see that we have a fair amount of the peak tailing happening for some of these peaks, and we got a lot of overlap on this one over here. Okay, had we carried out that same separation on an end cap column where we've reacted some of those silanol sites, okay, you can see that we're getting improved peak shape. Peak 5 here looks better. Peak 4 definitely looks better in terms of removing the tailing. So that is another option you have available to you when you purchase your column. Another decision one has to make is the particle diameter of the silica within the column. As we addressed in our previous lesson, an important parameter of the resolution of a separation has to do with band broadening. And if you will recall, we said that the band broadening that we measure, plate height, okay, it does depend on, it is a function of the particle diameter of the little spherical particles that we pack into the column. The smaller these particles are, the smaller their diameter, the more efficiently they pack, and the contribution to band broadening, it improves the band broadening. As this gets smaller, as we decrease the particle diameter, we decrease band broadening, which means we increase the number of theoretical plates, which means we enhance the resolution of our separation. So when giving consideration to the impacts of the particle diameter, the relationship of the particle diameter to the number of theoretical plates, remember N, we want to maximize. So as the particle diameter decreases, the number of theoretical plates go up. So ideally, we want to select our silica particles to have a small particle diameter. The most standard size is either 10 or 5 microns. The trouble with reducing the diameter of the particles, the smaller they get, the tighter they pack into the column, and there's less void volume between the particles. With less void volume between the particles, that's going to require a higher pressure to get the mobile phase to flow over the packed bed. So in terms of the effect of the particle diameter on the pressure required to get the mobile phase to flow over that column, okay, as these particles get smaller, okay, the required pressure goes up substantially. So you need to have an instrument that has pumps capable of getting flow in that magnitude. The impact on a separation for different particle size is illustrated to the left. We have a sample being separated on a C18 column, everything being held constant except the particle size. Okay. The figure A is when our particles are 4 microns in diameter, and the chromatogram for figure B is when we used 1.7 micron silica particles. You can see that the number of theoretical plates for the peak illustrated here is 2,000, whereas if we decrease the particle diameter, the peak is much narrower and number of theoretical plates is improved, 7,500. So that's a good illustration of what one can expect in terms of the impact of the width of your peaks with the selection of the diameter of the silica particles. This is just a summary of the impacts of the performance of a separation if we change the particle diameter. So we are looking at data for particles in which we're decreasing the particle diameter from 5 microns down to 1 micron. So first question, what does that do to the retention time? How long does it take to get a certain component off the column? So with bigger particles, it takes 30 minutes, the 5 micron column. If we had a 1 micron column, 6 minutes. So they're coming off faster. What does it do to the number of theoretical plates? With decreasing particle diameter, okay, we have increasing number of theoretical plates. So improved resolution. And as we predicted, the downside to all of this is what kind of pressure you're going to need to get your mobile phase to flow over a packed bed of these particles. Okay, so it's 19 bar for 5 micron particles, but 2300 for 1 micron particles. So that is ultra pressure reverse phase capillary liquid chromatography. And yet another choice one needs to make when you purchase a column for HPLC is the kind of silica in the column. So you have a choice of type A or type B silica. Type A tends to be the more acidic type of silica, and type B a lesser acidic silica. So on the silica surface, you have your silicon atoms sitting here at the surface with your attached and preferred R groups. Okay. And also on that surface, you can have unreacted silanol sites that tend to behave in an acidic manner. Once again, if you've got an amine group, something with an amine group in it, that's a base, there's going to be an attraction with the acidic silanol sites, so this is going to get hung up on the column longer. Okay. The other source of acidity on a silica surface is if you've got any metal ions affiliated with the surface. Such as that. So contamination, metal ions, can lead to acidity. So if you've got an oxygen adjacent to another silicon that has a metal group affiliated with it, it makes this oxygen even more electron withdrawing, making this group even more acidic. So if we can get rid of metal contamination off the surface, we're going to make this silanol site less acidic and behave as a lower acidity silica. So to get rid of the metal ions, we simply have to purify our silica more extensively. So many more steps in removing metal ions off the surface. So more steps means more money. So a type B silica is lower in acidity. Because we have exhaustively removed the metal ion contamination off the surface. So the advantage is it's likely going to give you better peak shape and less peak tailing, but it's going to cost you more. An example of an actual separation carried out for these drugs, and once again, all of these drugs and their structures, you're going to have amine groups that have the potential to do this kind of thing with any unreacted silanol sites. And so on the type A silica, which is the more acidic, less expensive, notice the shape of your peaks coming off. You do have a fair amount of tailing here for all of these peaks, and they tend to be fairly broad. If you were to have carried out the same separation on an octadecimal column that was type B silica instead of type A, once again, we've removed the metal ions, thus this electron withdrawing effect, making the silanol sites more acidic, has gone away, and you get much improved peak shape, less tailing, and narrower peaks. The next selection that one has to make in choosing our stationary phase material is the nature of the side groups. So initially, the attached silane compound that we put on our surface, we have our desirable R group, in this case an octadecyl, and the most common types of silanes that are attached to the surface are going to have methyl groups as the side groups. Those are fairly small structurally. If we have any unreacted silanol sites on the surface, such as the one depicted here, the access to that silanol site is going to be pretty easy. So if we don't intentionally put large side groups on our stationary phase material, we risk the access to the unreacted silanol sites. Once again, the disadvantage to that is if we are trying to separate a sample mixture in which there's pharmaceuticals or other types of molecules that have a basic functionality, they're going to tend to get hung up on those silanol sites and result in peak tailing. So that's one disadvantage to using the smaller side groups. Another disadvantage to having small side groups, we mentioned that sometimes we have to choose a separation in acidic conditions, low pH, and for good reason. Sometimes we want to have our species fully protonated. If our samples we're trying to separate have acidic groups, to keep that hydrogen ion on the molecule, we have to do that at low pH. Okay, so there's reasons why we would want to do a separation at low pH. The problem with that is hydronium ions can actually come in and attack the siloxane bond. If that happens and we lose some of our stationary phase off the surface of our column, then the column starts behaving differently. And all of our optimization that we did with our method development will go out the window. And we're going to have to replace the column. So that is very undesirable. So if we can protect somehow these siloxane bonds better, we can prevent that from happening. One way to prevent that, let me get rid of some of my drawing here. Okay, the best way to protect my siloxane bonds is, instead of putting on a methyl group as my side group, why don't I put something big and bulky, such as an isobutyl group? That will better protect my surface and block access to any unreacted silanol sites. That will avoid, to the extent possible, some of this peak tailing. And also, I will better protect my siloxane bonds and attack from hydronium ions under acidic conditions. So that is another option that one has when you choose your stationary phase material. Are you just going to go with a dimethyl functionality, or are you going to use sterically protected side groups? The downside with those is you may get less loading of the silane on the surface. So less stationary phase gives you less capacity. But if that's not an important factor, then you may want to choose a sterically protecting side group. The next consideration when choosing our stationary phase material, a recent discovery and patented technology is to intentionally embed a polar group into our long hydrophobic chain. So at the end of our group that we've attached, we still have our long carbon chain. So obviously this is still a C18 group out here. But instead of having that directly linked to the surface through our siloxane bond down here, we're going to intentionally put in a few carbons that are not saturated. So there's rotation and movement around those bonds. And then we're going to put an amide group here. And so obviously the amide group has an NH group. The nitrogen has a lone pair of electrons. Okay, remember on the surface, the silanol sites are acidic. The hydrogen is slightly positive. So this amide group, the nitrogen within it, is going to bend over and hydrogen bond down to this unreacted silanol site. So we're going to tie up our unreacted silanol sites intentionally so that my analyte species flowing through, my molecules of whatever species I'm trying to separate, so they will no longer have the opportunity to get stuck on those silanol sites and then result in peak tailing. So these polar embedded phases will result in improved chromatograms as shown to the right. We are first looking at a separation done on just a traditional C18 column without such a polar embedded phase. You will see for this particular separation, we have considerable peak tailing happening with each and every one of our components. Okay, so that is undesirable. If we had used a stationary phase material with this embedded amide group, in which it's going to bend over and tie up these unreacted silanol sites, we have much improved peak shape for each and every one of our components. So that is another option one can consider in purchasing your stationary phase material. We have yet another choice to make, and that is regard to the nature of the porosity of our silica particles. The traditional silica particle is totally porous. The pore structure is from the outer surface all the way to the inner surface of the particle, and that has several advantages, obviously. That gives us a huge surface area onto which we can attach our stationary phase material. And then the reality is our little analyte species, they penetrate down into the pores and they get caught up at different depths of the pores, and at some point they'll come back out, get caught up in the mobile phase, and come out. So the time that the analyte species spend going into the pore structure and then coming back out, okay, that times can be a problem if we're trying to get the separation to occur in as short a period of time as possible. So another way of dealing with that might be to limit the depth of our pore structure. So a patented technology that came out was something known as superficially porous particles, in which the pore structure only exists at a smaller depth on the outer silica surface, and at the center is just a solid core of silica with no pore structure. The advantages of that design of the particles is as follows. If we go to a Van Deemter plot in which we're optimizing the flow rate of our mobile phase, remember we want to minimize the plate height for the best resolution, so we're looking for the flow rate that gives us the minimum plate height. Okay, the first parameter we're looking at is the diameter of the particle in general. Okay, so 5 micron particles, and these are traditionally fully porous particles. 3.5 and 1.8 micron particles. So you will notice if our particles are 5 microns in diameter and totally porous, we get a minimum H plate height here at a flow rate of about 2 millimeters per second. Okay, the downside to this is, notice if I want to do my separation at a higher flow rate, I do so at lost resolution. So that's limiting. If I go to a smaller particle diameter, 3.5 microns, okay, and these are totally porous particles, I get an improved plate height, okay, so minimum plate height, and I get an improved range of flow rates that give me this ideal plate height. So now I have the option of using a faster flow rate, which can shorten my separation time. That continues if I reduce my particle diameter further down to 1.8 microns. And that's this last dark line here. I'll retrace it for you so you know which one we're looking at. Right there. And so here we get this minimum plate height, ideal resolution, over a nice range of flow rates. So that's advantageous. Now the disadvantage of tiny particles, remember, is the pressure that we need to push the mobile phase. We may not have an instrument that allows us to do ultra high pressure HPLC. So the superficially porous particles that has a more limited pore structure kind of gives us the best of both worlds. You will notice this light blue Van Deemter plot for the superficially porous particles. Okay, we get the advantage of optimal resolution. There's our minimum H right here, and it's consistent over these. Let me clear my writing so we can see what we're looking at. Okay, so my minimum H is here, but notice that it's low for this entire range of flow rates. And the advantage to my 2.7 micron superficially porous particle is it's not as tiny as this one, and I don't have to use as high a pressure to get flow over that particle. So I kind of get the best of both worlds. I get the advantage of being able to use faster flow rates without compromising resolution. This slide simply illustrates an actual separation chromatogram that was carried out on a superficially porous particle. Once again, the diameter of the particle is 5 microns in general, so I don't have to use super ultra high pressures to get flow over that packed bed, and I'm able to use faster flow rates because of the limited depth of the pore structure on the particle. Okay, so you can see I'm getting a nice clean separation for all of my components in a reasonable amount of time. To end our discussion of the options that we have in selecting our columns and the stationary phase materials within those columns is the state-of-the-art of where research is in regard to packed columns. Instead of having little particles that have big pore structures, as we've talked about recently, there's another strategy with creating a pore structure that has a large surface area that's not a bunch of little tiny particles that pack tightly into the column. The strategy is to get big pockets of open areas that will allow the flow of the mobile phase while still having a very large surface area here onto which we have attached our desirable stationary phase material. So monolithic columns are columns with this pore structure that grows up inside of the column without having little tiny particles. And so the big advantage, much reduced resistance to flow, so we don't need to have pumps that have to operate at such high pressures. We don't sacrifice surface area. We still have a very high surface area stationary phase structure, so we are not limiting the capacity of the column. And so we have kind of two sets of pore structures in here. You know, we have the big wide open 2 micron pores that allows the mobile phase to flow through easily, and then we have little tiny pores that improve that surface area.